Hello everyone, my name is Sarah Sqat and I'm going to present to you the paper entitled A Statistical Based Modeling Approach for Deep Learning Based Speech Emotion Recognition. As the presentation progresses, we'll be going through the more usual outline from the introduction to the conclusion. Well, speech emotion recognition refers to the process of automatically identifying the speaker's emotion from a given utterance. The use of speech emotion recognition technology has grown significantly since its introduction and has found applications in many areas. Among them, entertainment, where speech emotion recognition can be incorporated in the development of natural and interesting games with virtual reality experiences. Call centers, where tracking customers' emotional states can be useful for detecting deception or frustration. Also, in the field of medicine, for analysis and diagnosis of cognitive states of human beings. And in education, for instance, in affective e-learning, where speech emotion recognition can help to offer appropriate online feedback based upon learners' vocal intonations in order to foster their learning. Speech emotion recognition methods based on deep learning have gradually attracted the attention of researchers. They are mainly divided into two groups. We find those attempting to automate the feature extraction part of the recognition process, where networks are designed with the objective of detecting significant features directly from raw data, and those that perform a feature extraction or a particular representation of the speech signals before feeding the network. In this case, literature works focus on proposing deep two-dimensional or three-dimensional architectures or make use of one-dimensional networks with large feature sets as input. In our work, we concentrate in one hand on developing a speech emotion recognition system using a one-dimensional convolutional neural network, and in the other hand, we make use of a relatively low-dimensional feature set. In our approach, the considered input vector that is fed to the network is constructed by computing the mean values of the male frequency capsular coefficients over the time axis. The CNN architectures then consists of a total number of 3 layers, 2 convolutional layers and 1 fully connected layer. The number of filters in the convolutional layers is chosen to be 128 with a kernel size of 5. Max pooling is then added with a pool size of 8 in order to reduce the dimensionality, and dropout layers are added to reduce overfitting. In order to appraise the effectiveness of the proposed approach, investigations were conducted on the RAFDES database that regroups recordings of 24 professional actors speaking and signaling with various emotions. Thus, only speaking utterances were considered for this study. The database consists of 1,440 speech files. The speech files are labeled into 8 emotional states that are fear, disgust, happiness, calm, sadness, anger, surprise, in addition to neutral states. Experiments were carried out in a way to study the speaker dependency of the emotional recognition system. Accordingly, the evaluation was set up through an iterative random split validation procedure. The experimental data was then split into 2 sets randomly. The training set took 80% of the data and the remaining 20% were kept for testing. The CNN parameters were optimized using RMS-prop with an initial learning rate of 500,000. Also, we have used 1,000 epochs with batch size of 16. First, we report the average confusion matrix of the proposed model. From this, we can clearly show that the model confidently identifies the emotion of disgust with an average identification rate of 98.18%. followed by calm with an average accuracy of 94.12%. However, the lower identification rate of 53.33 is noticed for the emotion of surprise, which is mainly confused with happiness, with a percentage of 88.89%. Next, we position our results with respect to literature works. According to the obtained results, we can see that our proposed framework outperforms globally the literature works. Besides, by comparing our results with those of the work 31, we can say that our findings are slightly encouraging, as results show a gap of only 0.7%, with the difference that we use only the mean values of mean frequency capsular coefficients, while they used a unsupervised learning using the total mean frequency capsular coefficients matrix. Now, as we come to the end of this representation, let's recap what has been done in this paper. We have proposed the framework, a speech emotion recognition framework, to take full advantage of deep learning networks with extracted features as input data. In this context, we have computed the mean values of mean frequency capsular coefficients and use a one-dimensional convolutional neural network as classifier. Our experimental results globally outperformed the state-of-the-art works for a Ravides dataset in terms of simplicity, generality, and applicability. An identification rate of 79.59% was achieved for speaker-dependent experiments. Thank you for your attention.